Good morning, everyone. I would like to start the second day of the conference with the session 6A, electric vehicles. Unfortunately, the chair of the conference, due to unforeseen reason, couldn't take part in, and I am co-chair of the conference, substitute him. So I would like to invite the first presenter, Szymon Racewicz, to make the first presentation titled Quality Analysis of Welds Made with an Automatic Battery Pack Spot Welding Machine. So,
good morning again.
Morning.
Okay, it's good.
Yes, everything is fine.
So my name is Szymon Racewicz. I would like to present a subject dealing with quality analysis of welds made with an automatic battery pack spot welding machine. The presentation outline is as follows. At the beginning, a brief introduction. Then I will talk about principles of resistance spot welding process and quality assessment of welds, joints. Finally, I will describe the test bench and present the research results and conclude my presentation. The reason why the research has been undertaken is the growing interest in electric mobility, which we observe more and more since the last few decades. Especially one can notice that there is a huge interest in personal transport devices like electric scooters, for example, which are present in many cities, or self-designed electric bicycles made by their owners using conversion kits, which are widely available on the market. And of course, building an electric vehicle always entails the necessity of battery pack construction. For the personal transport devices, the battery packs are usually made of 18650 type battery cells connected with the packaging steel tape. And the joints between the cells and the tape are often done using resistance spot welding process. This process is very widespread in industry, but it is also relatively easy to build a self-designed spot welder using widely available elements. So there are many people who make the battery packs themselves in order to save some money, as the market prices of the ready-made batteries are relatively high. Unfortunately, we can hear more and more often about the uncontrolled fires of electric vehicles, which are very difficult to extinguish. Let me show you one of the many films available in the internet showing fire of an electric bike. It's here. Yeah, please. So we can see that the fire is very dynamic and can last for many minutes, depending on the battery size. And it's worth noting that the power density of lithium-ion cells is about 270 watt-hours per kilogram. So likely this fire is outside. Okay. So the yes. So the research objective, the most often causes of such a fire are internal short circuits. And so the quality of welded joints is then the crucial issue to ensure safe operation of an electric vehicle. In the literature, we can find the methods for an early detection of the internal so-called soft short circuits. Yeah, but our research focuses on preventing such an events by increasing the overall mechanical strength of the battery pack. So the research objective is formulated as investigation of the optimal preheat pulse time value set on the automatic spot resistance welding machine in terms of mechanical strength of the welds performed on the 18650 cell type using the experimental method. Here we have two constructions made in our laboratory for different tests. The resistance spot welding process consists on flowing of the high intensity current at the contact points of the electrodes with the materials to be bonded. The materials are heated to the melting points, and if they are pressed with an appropriate force, the weld is formed thanks to the solidification of the melted materials. And in the industry, we would rather find the spot welder constructions like shown in this figure. But for the cell welding, we use this kind of configuration. So the electrodes are next to each other, what in fact gives us two welds. Of course, this is a very complex process which requires consideration of many factors like maximal current, welding time, that is values of time pulses, which we investigated, number of the pulses, contact area, pressing force, distance between the electrodes, material and geometry of the electrodes, or characteristics of bonded materials, and so on. In our research, as I said, we have focused mainly on the welding time pulses and its influence of the weld strength, as this is the most adjustable factor during spot welding. It should be noted that there are also other methods for connecting two elements. These are, for example, soldering, but it involves using some kind of binder called solder. So it is more problematic, less safe, and more time consuming regarding battery packs production. Other methods which should be mentioned are laser beam welding or ultrasonic metal welding, but they also haven't found wider application in battery cell welding. Quality assessment of the welded joints. In order to verify the correctness and effectiveness of the welded joints, we can use several different methods. These are in general destructive tests, like peel test or tensile test, and non-destructive ones like visual testing, ultrasonographic, or magnetic or radiographic tests, which are not harmful to the tested sample. And there is also a third group. We can also use the simulation methods as well. And for example, finite element simulation method. And in our research, we have focused on the destructive testing, that is the tensile test, the breakage test, as we wanted to determine the best welder parameters in terms of the welded joint's strength. Okay, and so in order to investigate an influence of the welding parameters of the welds, the automatic spot resistance welding machine was designed and constructed. As you can see on the presented slide, it has a function of setting two welding time pulses or turning off the second pulse completely. The RMS value of the welding current was measured as about 643 amperes. and samples. The samples were prepared using different welding time pulses. Each sample was made in 3 copies to verify the repeatability of the measurements and elimination of the possible faulty samples. And this is gathered in the table. So for the time pulses below 40 milliseconds and 20 milliseconds, here, 40 milliseconds and 20, the proper welding process didn't occur, and the surfaces were just stacked together because there was no proper melting of the materials. On the other side, we have noticed that the single time pulse, which is greater than 120 milliseconds for our materials, for our conditions, caused dangerous burnouts, and the cell connectors were damaged. It is shown here. So this is the upper value of the time pulse, single time pulse. Finally, in order to determine the strength parameters of the prepared samples, the braking force measuring device was designed and prepared. It recorded the force exerted on the samples during stretching. The force was measured using tensometric beam here and visualized by telemetry viewer software. So passing to the results. Each sample was subjected to a breakage test, a tensile test, and I remind that we had 3 trials for each time pulse. These are 3 trials. And the highest recorded force during breakage was taken into account. And so these points. And based on these 3 values, an arithmetic mean and a standard deviation were calculated for the analysis. Here we have only 2 representative examples of the tensile forces curves chosen from many others. Of course, they all were practically the same, apart from the values, of course. I mean, shapes were almost the same. These different inclinations of the curves are not relevant to the research and are due to the lack of the motor speed controller. So at the load of about tens of newtons, the engine speed dropped slightly. So this is why the shapes are like that. Almost always both welds were broken at the same time. But as we can see here, sometimes one of the welds breaks as first and then the other. It is due either to an uneven pressing force of both electrodes, or it can also indicate the wear of one of the electrodes. So after adjusting the electrodes, this issue disappears. After a series of tests, we can notice that the preheat time pulse has a decisive influence of the weld strength. The second pulse does not improve significantly the overall mechanical strength of the welds. Moreover, the increase in the braking force is stabilizing, as we can see here. The maximum braking force obtained during the tests without cell damage was equal to 194.5 Newton for the current pulses of T1 80 milliseconds and T2 60 milliseconds on this one. Such a weld has sufficient mechanical strength for the battery pack construction purpose. To conclude, it has been shown that the preheat pulse time value has a crucial influence of the weld's mechanical strength. and the upper value of time pulse is limited by a thermal capacity of a cell connector. We also notice that the electrode's pressure is a significant factor in terms of welding conditions. It can be diagnosed by visual testing when there are visible surface defects in form or of uneven weld shapes. And one of the disadvantages of the proposed method is the necessity of sample preparation for the braking force measuring device, which can be of better quality compared to the welds which are made during the regular battery pack production. So thank you.
Okay, thank you. Do we have any questions from the audience? Okay, if no, so I would like to ask you probably two questions, or maybe one question with two possibilities. Okay, so from the manufacturer side, how many batteries could be packed into one pack based on your research?
How many battery? It depends on the size of the battery pack.
Yes, but let's say considering all your data which you obtained during your research, probably there is a limit. So, and you probably can provide recommendation. Yes.
In our spot welding machine, there was not a lot of batteries packed because it was just for testing. So this is the pack which is prepared by our spot welding machine. So it's 3 times 6 batteries just for verify by the visual testing to verify how the welds are made and to check also the strength. As what I wanted to say, at first I meant that how many batteries can be packed in the battery. Oh, here is our two constructions made, and so these are the e-bikes with a lot of battery packs. I don't remember the exact value, but it's tens of even about 100 batteries packed here, and here even more, as this engine has more than 3 kilowatts.
I see. Okay. And one more question about the quality of the battery pack. Let's say in one figure you showed that some batteries are connected with the same plate.
Yes, because the voltage of the one cell is 4.2, and if we have to obtain a battery which has 48 volts, for example, like in our bicycles, we have to connect the cells in series and in parallel. Okay. So we connect the cells in series and then in parallel to obtain more current.
Okay. So have you evaluated, let's say, what may happen if you use different plates for each pair of batteries? I mean, not one plate for, let's say, for 5 batteries, but you use separate small plates for 2 batteries, then 2 and 2 and 2, and it overlaps.
No, because the practice is that we use the one stripe. It's better to use one stripe.
Yeah, but
from the mechanical point of view, and for spot resistance welding, it would be more difficult to make a weld by the 3 layers.
Yes, I'm thinking about possibility to repair after some time. Let's say.
Yes, it's possible, but normally we can. If the connection is broken, we can replace the battery, and we can even make welds again on the same battery, the connector of the battery is usually more resistive than this steel tape. So if the steel tape is still in good condition, we can reuse this steel tape.
I see.
And if it's, of course, if it's broken, as you said, we can cut and replace. But I would rather recommend to replace all the stripe.
Okay. Okay. So thank you for the presentation.
Thank you.
And I would like to invite the second presenter, Gergana Vacheva, if I pronounce well, the presentation, model-based evaluation of energy consumption in hybrid electric vehicles.
Yes, thank you, Mr. Chairman. I will share my screen. Just a second. So, dear colleagues, my name is Gergana. Thank you. My name is Gergana Vacheva, and today I will present you our paper, which is entitled Model-Based Evaluation of Energy Consumption in Hybrid Electric Vehicle. Me and my colleagues were from Technical University of Sofia, Department of Power Electronics. Briefly, I will show you the basic problems which is in front of us when we talk about the electric vehicles. So as briefly introduction of the problem, we all know that we have a lot of increased harmful emission and changing of the climate in multiple cities in Europe and in the world. So we have to take some drastic measure for limitation of this harmful emission. And one of the reasons is to develop some solution which is appropriate for diminution of this harmful emissions. So the first of all the things is to essentially make some transition from internal combustion engines of the standard vehicle to hybrid vehicle when we used additional battery and additional motor, which is for the start of the vehicle. So this is briefly our purpose here, to make some evaluation of the energy consumption in different driving cycles, which is provided by the different by the European Commission. So here we have some basic table in which are presented the level of hybridization. So here we have the different type of vehicles, hybrid vehicles, of course, and also the electric vehicle, which is only with the different type of electric motor. So here we have micro hybrids. Here is presented the traction force, and also here we have the percentage of the gasoline or diesel. This is the motor of internal combustion motor. So here, when we have pure electric vehicle, we have only usage of batteries, but in our case, we make some examination of hybrid electric vehicle. Here we have presented the two basic architecture of the vehicle, of the hybrid vehicle. So here we have series drive and parallel. So the basic idea here is presented the box scheme of the typical hybrid and typical parallel vehicle. So here we have the mechanical connection, which is here from the engine to the generator. Also, we have the electrical power, which is presented with only one line. And also we have all the signals. This is all the control, which is for control the energy, the currents, the voltages, and all the things which is included in this structure. So here the basic difference, we have the series in which is connected in series all the engine and generator, and also the electric motor. Here also we can see the transmission which is connected to the wheels. When we have parallel connection, we connect the internal combustion engine with the electric motor in parallel, so the both they can work in the both way. So here is presented the different driving cycles which we use. This is a standardized driving cycle which is provided from the European Commission. So here the first one is the newest, which is used for electric vehicle, and here we have the amendment of the time and also the amendment of the the amendment of the speed in the function of the time, and this is presented in the kilometer per hour. In our case here we have presented in meter per seconds. This is the other two. This is another one which is used here is from Europe. This is one from America, which is used. This is standard, and with this driving cycle, we can make some evaluation of the energy and the fuel which is used for drive some hybrid vehicle. And so here we have presented, this is the basic question which describe the movement of the vehicle. In our case, we mathematically use the forces, the traction forces, which is this is the sum of all the forces, traction forces, which is for the electric motor, and also here is presented all the sum of all the forces, which is aerodynamic forces, the forces from frotment, and also the mass of the vehicle. So also we have some table in which is presented the parameters of hybrid electric vehicle. We used standard one which we take from manufacturer. So here we have the mass of the vehicle, the rotating mass, the vehicle cross section which is used in these forces, the diameter of the wheel, the drag coefficient, and also rolling friction coefficient, which is used in which is implemented here in all the forces which affect of the vehicle. And here we realized in MATLAB Simulink this model in which we have some internal combustion engine, also electric motor, and battery. And in our case, the initial value of the state of charge of the battery is 20% in this examination. And here we add these three different driving cycles. So we have the combustion engine. Here we can see how much is the fuel consumption. And here is all the transmission which is connected from the electric motor. So this is our model, and also we can measure the power from the battery, the current charge of the battery, the energy consumption by the battery, and also by the engine, the internal combustion engine, and the total. Of course, we added as a reference, as I said, total distance. So that depends of the type of the driving cycle. So here we obtain some simulation results. In the first figure, we have the power of the battery, which is here. This is the power from battery, the current charge of the battery, the energy consumption by the battery, and also we have the total distance. In our case, we are realizing in three different driving cycles. So here we have VOTC class 3 because it exists also VOTC class 1 and class 3, which is the difference between them is that they're also the city driving cycles with multiple brakings and startings of the vehicle, but we have the different amendment of the velocity. So here we made the same simulation results with the different driving cycles to examine in which case is we obtain the better and minimal usage of the electric vehicle, of the electric motor, and also the minimum fuel consumption. So also we have this is here is presented the third driving cycle. So also we can see the power from the engine, the energy consumption, and also the total distance. And here in this table, we are presented the summarized results from the different, the three different driving cycles. So here we have the power from the engines. We have the average value, which is presented for the power of the engine, which is used in this model. Also, we have the minimum and the maximum value of this power. Also, we have the usage of the battery in kilowatt, also the energy consumption by engine, that means in liter per 100 kilometers. Here is presented for the three different driving cycles. Also, we have the energy consumption by the battery in the kilowatt hour per 100 kilometer, and here is presented the total distance, which is in kilometers in this case. What we can say as a discussion of this problem, so in this studies we realize typical series hybrid configuration, which is useful for estimation of the energy consumption of the battery and the fuel consumption, of course. We can see that there's significant difference in consumption for the different urban traffic cycles. So in this presented table, the negative value represent the supplied power from the battery, and also we can see that in our case is used at least in the FTP 75 driving cycles, in which case the higher average fuel consumption is also evident. So it is 28% larger with FTP compared to VOTC. That means that this is because this is the greater use of the power, battery power in VOTC, which is 36% more than FTP. As a comparison that we can see, an intercity traffic cycle has been added with not so frequent braking and starts. That means that we have not so much amendment of the velocity, and we don't have so frequent braking and starts. So also due to the HW FET cycle type, higher battery usage is observed, which is due to the almost constant amendment of the velocity. So in our future research, we mean to also make some examination of the similar results of different type of hybrid vehicles. That means different in the different architecture, of course, because in this case is presented only the series 1. And as a discussion, as a conclusion, I can say that in our paper we realized some evaluation of energy consumption of typical hybrid vehicle. The model is realized in MATLAB Simulink and also is used QSS toolbox, which is implemented in MATLAB. And we used typical data for hybrid vehicle as a mass, aerodynamic drag, tire size, and all the another characteristic of the hybrid vehicle. So we made our examination with three different driving cycles, VLTC, HWFET, and FTP75, which is standardized driving cycle. And our research is useful for usage in when we have study energy demands of different type of hybrid, and also in electric vehicle. Also, we can make the same solution when we have, for example, two electric motors. So in this case, we can make some evaluation of the work exactly of this type of vehicle. So this is basically our work. So thank you for your attention. If you have some question.
Okay, thank you. So maybe someone would like to ask from the presentation. Okay, so I would like to ask you one question.
Yes.
About the model which you used.
Yes.
So you used only some data to create the model, or how many parameters you try to estimate in your model? Is it wide range or just couple and basic parameters?
Here is presented. I can made it here. So here we have the wheel, the torque, the size of the wheel, also the torque which is presented, the amendment of the velocity. We have the transmission also. That means that we have in our model 5 transmission in which we have the different coefficients. So we added this transmission also, and also we have the characteristic of the electric motor. In our case, here I think it's.
And what about let's say other conditions like friction, like wind? Have you estimated them, or it was under perfect conditions?
The friction is implemented as a coefficient. The wind, not exactly, because it has different across, to say, wind, which is not implemented in this model. We take only the aerodynamic force, in which is included the density of the air.
Oh. Okay.
Thank you.
Okay, thank you for the presentation.
Thank you.
And I would like to invite the first presenter in this session. So it's Marek Pastor. Marek? Oh, okay. So
good morning, ladies and gentlemen.
Good morning. So please introduce your title and of the presentation, and please go on.
Thank you, Mr. Chairman, for introduction. I just need to start sharing my screen. So my name is Marek Pastor. I'm from Technical University of Košice in Slovakia, and the paper I will present deals with design and measurements of a frequency converter for a two-phase induction motor. Maybe like the first question is like, why two-phase motor? So I will present the motivation for two-phase induction motor. Then I will talk about converter topologies, which are useful or can be used for two-phase induction motor frequency converter. Then shortly about the design converter and measurement setup, measurement results, and then some conclusions and ideas for future work. Our department has a long tradition in electrical drives, and my colleagues sometimes get bored with traditional three-phase induction machines. So they start a project with some motors which have odd numbers of phases, like two-phase motor, which is presented here. We also had project with five-phase induction machine. So two-phase induction machine is in general the simplest multi-phase induction motor. It has just two windings, and the motor which was used for the experiments and for measurements was built from washing machine motor. A washing machine motor has it's a single phase motor which has two windings, main winding and one auxiliary winding. So the motor was rebuilt, so it has two identical windings which are winded like is shown on a figure 2. The parameters of a motor, well, its output power is rather small. It has 120 watts. The nominal speed was 2,580 rotations per minute, and the torque was just 0.44 Newton meters. Converters for two-phase induction machines, there are three possibilities. First one is a half-bridge converter. It's the simplest one. You see that it powers the two windings of an induction machine with half of the supply voltage, so that supply voltage VDC is divided by 2. The next one is a two-phase three-leg converter. By adding 2 more switches, the converter gets a bit more complicated, but the advantage is that it can power the two windings of the induction machine by the full DC link voltage. And the last one, the most complicated, is a two-phase H-bridge converter, when each winding of the induction machine is supplied by a dedicated H-bridge converter, and it gives the widest possibilities for the optimization and the unipolar or bipolar modulation used for the control of the machine. The converter topology that was used in our project is just that simplest one, two-phase half-bridge converter. The main motivation was because that motor is rather simple. It has just two windings. Then let's build a converter that is the simplest one as well. So it uses only 4 IGBT transistors and just a simple single-phase bridge rectifier. The control creates two voltages, U1 and U2, which are described by those two equations. The coefficient Km is the amplitude modulation ratio. So by changing it from 0 to 1, we apply the sinusoidal PWM modulation with a constant ratio between the RMS value of the voltage and the frequency. To model a two-phase machine, it's quite simple, because if you use alpha beta system, then you have main winding and auxiliary winding, so they are perpendicular to each other. So the same is valid for stator and for the rotor. Scheme of the converter, it's quite simple, just like 4 IGBT transistors. I just see that there is a mistake. It's taken from a diploma thesis. There are MOSFET transistors. There should be IGBTs. Power supply is divided into half, so the DC link voltage is split between two DC link capacitors, and the motor has 3 inputs. To control the converter, we use the DSP from Texas Instruments, and to create some isolation between the control system and the transistors, there is a optocoupler used, and there are 2 drivers, so which are using bootstrap technology to supply the upper MOS or upper IGBT transistor. Here is a picture of the built converter. So in the upper part, you see the 4 IGBTs. Below is a driver circuit with galvanic isolation, the optocouplers, and there is also an evaluation board with Texas Instruments digital signal processor. For the measurement, the DC link voltage, or the half of the DC link voltage, was set to 110 volts. We use oscilloscope and power analyzer to measure the RMS values of the voltages applied to the motor and to record the waveforms of the voltage and current of the motor. We use the bipolar switching, so the voltage applied to the motor was bipolar. The first setup was set for the frequency of the supply voltage to be 50 Hertz and the switching frequency of the converter. That 50 Hertz means it's a fundamental frequency of the first harmonic, and 2 kilohertz was the switching frequency of the IGBTs. You see the waveforms of the motor voltages. There are two-phase voltages. The RMS values of those voltages were set to, or were 38 volts RMS. The rotational speed of the motor was 2,800 RPMs, and on the figure 13 you can see the phase currents. They are rather small because the output power of the motor is also rather small, but you see some current ripple, as was expected, because that switching frequency was quite low. To verify a higher switching frequency, we also changed the frequency of the fundamental voltage applied to the motor to 100 Hertz, because the rotational speed of the induction motor depends on the frequency. The rotational speed increased to 5,800 RPMs, also due to constant voltage over frequency ratio. The voltages applied to the motor increased to 72 volts RMS. As was expected, the current ripple of the two motor currents decreased. You see that the waveforms are smoother than was for 2 kilohertz, as was expected. Again, just like bipolar modulation was used, because the bridge that we built doesn't allow unipolar modulation. So that's like quite simple presentation, because the work was quite simple. We just built a converter for two-phase induction motor with the power up to 500 watts. Half bridge topology was with bipolar switching was used due to its really simple design and the minimum number of switches. In the next research or investigation, we can change the topology to the H bridge topology, which is capable of providing unipolar switching. Unipolar switching will virtually increase the switching frequency twice, and it will further decrease the current ripple. IGBT transistors, no new technologies like GaN or SiC MOSFETs were used, and the Texas Instruments DSP is a standard in motor control applications. And the verified operation was verified by measurement on a motor. So thank you for attention, and if you have any questions, I'm ready to answer them.
Okay, thank you. Do we have any questions? Oh, so I would like to ask you about the efficiency. Have you tried to estimate it?
Well, that power analyzer is capable of measuring the efficiency. However, the efficiency wasn't measured because the efficiency of the converter would be rather high, I think, because there is no high switching frequency, and the currents like 200 milliamps, it's so low that also conduction losses are rather low. And to the efficiency of the two-phase induction machine, well, it's a quite interesting question, but I'm not the motor guy, I'm power electronic guy, so I can't answer it. But well, it's like good motivation. Maybe that two-phase machine could have higher efficiency, but I think that in general, three-phase machines have higher efficiency than two-phase machines. Yeah, so.
Definitely. Okay. Okay, thank you.
Thank you as well.
And I would like to ask to come back Gergana Vacheva to make the second presentation.
Thank you, Mr. Chairman. Just a second to share my screen. So it's okay? Maybe not.
Not yet. Okay.
Okay.
Now it's
Thank
okay.
So I will present our second paper, our second examination, which is entitled Modeling and Simulation of Induction Machine for Control of Energy Flow in Electric Vehicle. So here we have basically, I will not talk about all the things, but we realized a model of induction motor. In our model here we realized the presented scheme, in which we have equivalent scheme of the induction motor. This is standard scheme, and we are trying to realize a model in which two induction motor are coupled, and the idea is to realize the physical bench after this simulation, to realize physical bench of to examine all the energy flow, all the current and voltages in this bench. So here in our model, the effect of hysteresis and eddy currents and mechanical losses are neglected. The machine works in an unsaturated magnetic system, and there is proportionality between current and flux. Also, the stator and rotor winding are symmetrical, and the air gap is uniform, and current electromotive voltage and magnetic flux are sinusoidal. Here we have some mathematical equation. This is working principle, which is described with this equation. So also we have the power which is consumed, also electromagnetic moment in which we realized, we described all the things, and also we have, after the transformation, we have the slip SK, which is included in our mathematical model. So here we have the standard equation, which is present the modeling of the electric vehicle. We used the traction force, the aerodynamic force, and the rolling force, and also the equivalent mass of the vehicle. Here is presented in this picture the dynamic of the vehicle, which is included in our model. So we have here the force, aerodynamic force here, Fa, and the friction force and the rolling force. So here is our model. We have the induction motor drive that also, which is included. This is the second. The first model is induction motor, and the second one is couplet permanent magnet synchronous machine, which is the Welds of the first one, and they are coupled, and the idea is to connect all the characteristic of the vehicle as a Welds of the first induction motor. This is our model, and here we are implemented direct. We can see the electromagnetic torque, the speed, reference the speed of the motor also, and as simulation results we are obtained. We used also some driving cycles, the amendment of these driving cycles. We can see the reference and the measure from the simulation. So the blue one is the reference, and the red one is the measured from our simulation. So also we have the car vehicle speed, velocity in kilometer per hours. Also we have presented the motor speed, and also we have the motor current of the induction motor. Also, we have presented the electromagnetic torque of the induction motor, and how exactly is amendment the dynamic of the vehicle in Newton per meter. Also, we have the voltage of the motor and the current of the motor, which is presented here in this simulation. And as discussion that what can I say, that the control of the induction motor in the last few decades has been very well developed. So they have relatively simple construction and they are cheaper than other motors. Despite these advantages, it exists right now few electric vehicle manufacturers which are used asynchronous motor. And interesting thing that could be useful in the study is to present the energy flow in the electric vehicle, which is realized, which is driven by asynchronous motor. So we use standard applicable inverter for control of the implemented system. And also we can observe the control methods which is assigned to this model. So our idea is to verify to construct the physical bench after this simulation results and to construct physical bench with two couplet electric motor to see exactly the difference between the simulation and the physical research. So as a conclusion, I can say that we are presenting simulation study of the induction motor, which is coupled with a permanent magnet synchronous machine. In the model of the machine, of the permanent magnet synchronous machine is presented, included the dynamic of the electric vehicle with all the forces which react to the electric vehicle. Also is at the drag forces, which is act with a wider range for modeling. So in our case, we used driving cycle VOTC class 3, which is provided from the European Commission, and also the model is realized in MATLAB simulating. So we can see the how exactly is changed the voltages, the current of the motor. So this is briefly our study. So if you have, thank you for your attention, and if you have some question.
Okay. So do we have any questions from the audience? Probably no, I can't see any raised hands. Okay, so I would like to ask you about dynamic of the electric vehicle, how it was estimated. Actually, you showed that the graph, the figure about electromagnetic torque of induction motor, and how it was estimated, that dynamic.
We use this equation, which is for the force, and how exactly is amendment the forces of the vehicle, and after that we implement it as a load, and we use the torque for control this the moment for control the electric motor.
Is it possible to achieve such a dynamic effect in reality in our daily life?
I think that because we used some data which is standard for electric vehicle as a mass which is provided by the manufacturer. It exists different sites, online sites, in which we can see the mass, the torque of the vehicle.
And in the figures you showed, what is on the axis? What kind of labels? Is it time? Let's say it was around 1,000, 1,400. So was it time in seconds or?
It's seconds. In seconds, yes. It's around.
Okay.
This is provided. This is standard driving cycle. One type. So this is the time in which we have amendment of the velocity.
I see. Okay.
Thank you.
So thank you. And the last presenter left. So I would like to invite Austia Dapkuti to make her presentation.
Hello, everyone. Let me share my screen. It's good. You can see it, right?
Not in full screen. Oh, now it's good. Okay.
Okay. So title of our paper is Virtual Power Plant as a Tool for Cost-Reflective Network Charging Tariff. It's a bit different than the previous presentations that we had today. And firstly, I would like to acknowledge that this research is supported by the Norwegian financial mechanism and the state budget of the Republic of Lithuania as Norway grants. And this virtual power plant functionality is implemented in a SaaS cloud platform as unique functionality that was created during this Norway grants finance project. And more information about the project can be found at our websites at digitaltwin4industry.com and at our platform SaaS.net, which is operating actually right now, and you can try out the platform by yourselves. So this research firstly started as my master's thesis. And it was proposed by my colleagues at Energy Advice, who are also co-authors of this article. And at our company, at Energy Advice, we develop innovative digital solutions seeking to help companies achieve their CO2 emission targets and energy efficiency. And here we try to combine our knowledge in energy and IT sectors to propose novel and effective digital solutions like digital twins and now as virtual power plants. So, of course, emergence of fresh perspectives and novel ideas can sometimes appear as challenging and can trigger negative bias or resistance towards their adoptions, especially national energy regulatory institutions due to complex regulatory mechanisms. And I have encountered it as well while doing my master's. But talking about the current situation for prosumers in Lithuania at June of 2023, now there is a total of 708 megawatts of installed capacity, of which 590 are on site. And 118 megawatts are on rental platforms. So in Lithuania, there are new possibilities like wind and solar park rental platforms. And household members can rent out a part of solar or wind power plant in exchange for a portion of electricity generated. And it is open to any household. And as I discovered during my research, the net metering and traditional network charging that are adopted right now in Lithuania creates challenges for both operators and prosumers. One of them being that under current regulations of charging, it's not financially appealing for prosumers to install a higher capacity of solar power plant than needed for self-demand, and for operators, as self-sufficient prosumers decrease the amount of electricity purchased from the operator, it results in lower revenue collected, while prosumers generate additional costs for operators. So we can understand the challenges of traditional cost-reflective charging by looking at this scheme. So here's a fragment of electrical network. Here's the system side, high voltage level, medium voltage level, and low voltage level. And if you look at prosumer 2, in case there's a generation surplus, this generated energy close to a nearby residential consumer free, and this is the actual energy flow, and it creates costs in the network. But actually, energy is consumed locally, but the consumer is charged for a full price, and it consists of tariffs, including medium voltage level and high voltage level, even though he used actual energy locally and actually created lower cost. So this kind of charging does not encourage sustainable development and effective usage of the network, because generation must be coordinated with consumption, especially when installing new capacities. So virtual power plant solves these challenges. Here marked with this dashed line is virtual power plant data flow, and virtual power plant uses existent infrastructure, and it enables smart energy trade. Trying to address this challenge, and prosumers sells energy to the virtual power plant, and consumers buys it from a virtual power plant. And virtual power plant is virtual infrastructure, so it means that it's not limited geographically, and it allows this optimal energy trade. And for example, if energy price is lower at some further part of the network, it's possible for a virtual power plant to connect and buy and trade energy with that region. So here's a short overview of and general idea how virtual power plant can utilize this cost reflective charging and cost optimization. So as I mentioned before, and how we can see from these first and second equations, traditional charging takes into account the cost of the whole network, including the low, medium, and high voltages, and each cost generated in those parts have a tariff, and that tariff is usually determined for a long period of time, usually for a year. But we can determine the actual cost that occurred, that was created by the prosumer, by knowing the losses in the network, as can be seen from this equation. And generally, when we can determine these losses, we can make the price components variable, and then we can optimize them by utilizing optimal control of the virtual power plant operations. So here's a basic principle of implementation of a system that we created as SaaS Cloud Virtual Power Plant. So firstly, SaaS Cloud collects needed data. So meteorological data and market data are as services, and are already at the platform that I mentioned. Consumption data for consumers is collected from smart meter devices, and also technological data must be inserted in a model that describes the network equipment, etc. And then at first there are forecasting modules, and the energy demand is forecasted, also generation of renewables, and market prices forecasted. And there is decision optimization stage, and the energy balance is calculated, and the target of it is to have that generation matches the consumption, and the cost is minimum. So this energy balance can be calculated at 5 minute, 15 minute, and 1 hour time steps intervals, or at a custom intervals if needed. And once it's calculated and the station is validated, we can see based on the forecast what are the options. So if generation is will be higher than consumption, we can charge the batteries or sell surplus generation to market. Or if generation is lower, we can discharge batteries, buy energy from market, from a network, or use own resources. So once we know the forecast and we evaluate, estimate the station, we can calculate the costs for each of the source and also for the network operation, and can calculate the profit. And based on that, we can select the optimal control. What to do? We can also use not renewables, but other sources like diesel generator if needed, or buy energy from the network. And based on selected operation mode, the variable cost reflected charging is also enabled, and we can calculate the tariff for the energy itself and from the network usage, and for the price of the whole virtual power plant operation. And we can have a tariff for connected prosumers and for connected consumers. So here's briefly about the IT infrastructure of created SS Cloud virtual power plant platform. So we have developed a data collector software, and it's responsible for collecting data, and that data can be read from various meters, production control units, SCADAs, SQL servers, or softwares. And it can be read at needed frequency and from various protocols, including some of the most popular, most used protocols as the Modbus, MBus, RapidMQ, and other. And it's sent to the cloud where calculations are performed. And in the cloud, calculations are performed as scheduled tasks, and they are scheduled through Apache Airflow Scheduler. So conclusions of our study is that implementing cost-reflective charging tariffs through virtual power plants enables accurate evaluation, firstly, of network costs, and it can reduce the tax burden on both prosumers and consumers. And virtual power plants have a potential to optimize network costs and thus promote sustainable energy sector development. And government-supported virtual power plant schemes can attract private capital in this way, as I mentioned, because right now it's not very financially good to install higher capacity than you need for your own needs. It can increase the number of distributed power plants and reduce electricity prices in the market. And there are technical possibilities right now, such as well virtual power plant system, but currently those technical possibilities are not implemented in Lithuanian practice due to legal regulations and lack of laws currently just. And further research is needed to evaluate the impact of smart energy management on electricity spot prices, because if we can evaluate the situation and we can consume energy accordingly, it should change the electricity spot price. So thank you. And do you have any questions? I would be happy to answer them.
Okay, thank you. So do we have any questions from the audience? No, no questions. So I would like to ask you about control. What may happen, let's say, if there is a high demand of the energy and there is a limit of energy in the grid. And is this model could be applied in such situation, let's say somehow decrease the consumption of energy in some infrastructure objects or no, or just you?
Yes. Yes, the general idea is that it can decrease the consumption.
And how?
One of the components of the virtual power plants are usually the controllable loads. I'm not very familiar with what they are in the industry, but I know that it's possible. And also that's why you need to perform forecasting to know and to prepare for what's going to happen in the future.
Mm-hmm.
But yeah, maybe if in the whole grid there's a lack of energy, it should be an option to decrease consumption. But in the real operation, I think virtual power plants are not like that. It's not going to be like, it's not going to cover a big part of the network. So it should be able to purchase energy from an operator.
Mm-hmm. Okay.
If it's not possible to cover by your own resources, and in some instances it may be even cheaper. So the whole idea is to select the optimal solution.
I see. And how many virtual network operators could be assigned in your model, or there is an unlimited number?
Actually, I'm not sure right now. The operators.
Can we have, let's say, 10 or 20?
Operators, you mean like the network operators, like not persons.
Yeah. Not people.
I'm not sure how scalable it is, because as I mentioned, it's in practice it's not possible to try out, because there are no legal basis right now, not regulatory. But I think the system should be pretty scalable. It must be able to scale it and connect more network operators.
Okay, so thank you.
Thank you.
I would like to thank you to all the presenters for their presentations today in the earliest session. And now is a technical break until next session starts. So thank you and see you in the next session, I hope.